Hello junior chem students. In this video what we're going to do is we're going to go through the other two versions of the integrated rate law, specifically the second and zeroth order rate laws for integrated rate laws. We saw first order in class, and we're going to finish this up with second and zeroth. To be a little bit more specific about it, we're going to be covering pages 577 to pages 583 of stuff you can find in the textbook if you want to have the textbook handy. So just to remind you, integrated rate laws, what we can now do is correlate the concentration to time. So we can ask and answer questions such as how much reagent, how much reactant is going to be left after 10 minutes of a reaction. Once we know whether it's first, second, or zeroth order, we're going to have a series of equations that come out of calculus that will help us answer that kind of a question. Pretty powerful question. So again, we did first order in class. Let's pick up the conversation with second order. And the idea here is that going into this calculus, we know that the rate law is second order. In other words, we know that the rate is equal to some rate constant times the concentration of A squared. So we know it's second order. Perhaps we did a method of initial rates type experiment and we were able to determine that when you double the concentration of A, you actually quadruple the rate. And so that would be a second order reaction. So as I mentioned in class, if you can understand the calculus, that's great. If this stuff may be a little bit confusing to you, that's okay. What we're going to care about, what we're going to hold you responsible for being able to manipulate, is the stuff that's going to be in the boxes of all of these slides. So for second order, we have rate is equal to the loss of concentration of A over the change in time, and that will be equal to Ka squared now since it's second order. So as we discussed in class, to turn this into some calculus, we go from big changes, deltas, to little changes, d. So we'll have dA dt is equal to negative Ka squared, and we just drop the brackets to get a little bit lazy. Rearrange this equation so we have all similar terms on the same side of the equal sign, and we get dA over A squared is equal to negative K dt. Then we're going to integrate both sides of this equality with respect to the variable. So we're going to integrate A from A0 to some time A that we'll call later, and that'll be equal to the experiment at the beginning, time 0 to time t that we integrate with respect to dt. So calculus fans, maybe you remember the integration of 1 over x squared dx is equal to negative 1 over x, and that's what we see over here with respect to the concentration of A. So the left-hand side of this integration becomes negative 1 over A minus negative 1 over A0 or plus 1 over A0. Then we integrate dt from time t down to time 0. The time 0 just falls off, and the right-hand side becomes negative kt. Just rearranging this so that it has the same form of the equation that we saw for first order, namely, we want to represent this in a straight line format, y equals mx plus b. So I have 1 over a equals kt plus 1 over a0. So if I were to graph 1 over A versus time, I would get a straight line. So this applies to second order reactions only. 1 over A equals KT plus 1 over A0. Just like we did for first order, let's take a look and see what the corresponding half-life equation will be for a second order reaction. Remember that half-life is the time it takes to get down to 50% of the initial reagent consumed. So for half-life for second order, at time half-life, we have A equals A0 over 2. So we're at the 50% complete mark. So I'm simply going to plug in A0 over 2 in for A and solve for T. All right, the algebra gets a little messy here because we're dealing with fractions, but we get 2 over A0 minus 1 over A0 is equal to KT 1/2 now, because I'm specifically at the half-life, solve that left-hand side, and we get 1 over a0 equals k t1 half. Solve for t1 half, and we get 1 over k a0. Now, I want to pause here because we have an interesting thing to consider here. You'll recall for first-order half-life, the equation is the natural log of 2, which is 0.693 divided by k. First-order half-lives are a constant. So to go from 100% of stuff to 50% of stuff is 1 time in first order. To go from 50% of your reagent down to 25% of your reagent is the exact same amount of time because half-life is constant for first order. For second order, what we see here is that the a0 term makes an appearance. This tells us that each consecutive half-life will not be the same as the previous half-life. It's not constant. Specifically, it's not constant because each successive half-life will be 2 times the previous half-life, because the new a0 is 1/2 the previous a0. So if your first half-life was 10 minutes, for example, the next half-life, the second half-life for second order, would be 20 minutes. The third half-life would be 40 minutes, etc., etc., etc. So it's almost like the reaction slowing down when you go from one half-life to the next. All right, so that is second-order details. Take a look at the corresponding equations for zeroth order. So now we have rate is equal to k times the concentration of A to the 0. Okay, k times A to the concentration of A to the 0. In other words, the reaction rate doesn't depend upon the concentration of whatever A may be. This is a little bit of an unusual circumstance, and we'll talk about in class situations that behave like this, but rest assured there are real-world situations that do this. So the calculus again, we have rate equals negative change in A divided by change in time equals KA0. Change your big changes to little changes, so deltas to D, and we have dA over dt equals negative K, because the A to the 0 just becomes 1, of course. Rearrange this so we get all the A's on the left-hand side and the dt on the right-hand side. We have dA equals negative K dt. And then we do the integration with respect to the variable, so A goes from the initial concentration of A0 to A at some time later. Time goes from the beginning of the experiment, time 0, to some time later, t. And the integral of dx is simply x. So the left-hand side of the equation, evaluated at the limits of the integration, is A minus A0 equals negative kt minus 0, and we just leave the 0 off. Rearranging so that this looks like y equals mx plus b, and we have A equals negative kt plus A0. So if you were to graph then the concentration of A versus time and get a straight line with a negative slope as seen by that negative sign there, that would tell you that your reaction is zeroth order. All right, what are we going to do next? Did you guess? And you're right. Once again, we'll plug in A0 over 2 into A for the corresponding zeroth order equation. Solve for T1 half, and we see T1 half equals A0 over 2K. Now, like second order, A0 makes an appearance in the half-life equation, so each consecutive half-life is not going to be a constant. And since A0, the second A0, is 1/2 the first A0, the T1 halves are getting shorter. So it's almost like this reaction speeds up as it goes along. Okay? So, let all of this information together in one handy-dandy little chart. And you can find a very similar chart on page 583 of the textbook. All I'm going to do here is summarize the first, second, and zeroth order equations we just developed. And for each one, I'm going to write out the corresponding equation. So for first order, we might write, for example, A equals A0 e to the minus kt. The straight line relationship is the natural log of A versus time for first order. And first order half-life is 0.693, the natural log of 2, divided by the rate constant k. For second order, we're going to have 1 over A0 is going to be equal to kt plus 1 over A0. Sorry, that first A0 there shouldn't be there. That's 1 over A. Our straight line relationship, 1 over A versus time. And then the half-life for second order is 1 over Ka0. And then 0th order reactions, we have A equals negative Kt plus A0. The straight line relationship is A versus time, and the half-life is A0 over 2K. So, more or less, if you can master the details of this summary slide without having to worry yourself about being able to work through the calculus, it's really this summary slide that we're going to be able to ask you to work with. And again, you can find this on page 583 if you want to see it in a slightly different format. All right, so before you come into class on Thursday, we're going to need you to do a few things, Thursday or Friday, to do a few things. First, I want you to work through a couple of practice problems. Okay, here's practice problem number 1. You might want to pause the video here in a couple of minutes so that you have some time to do it. But here we have a reaction as second order with respect to some reagent A. The half-life for the reaction is 2 seconds when A0 equals 0.9 molar. So you're going to need to find the value of K, and then you're going to need to tell us how much time it takes for A to be cut down to 0.1 molar. So this is second order. So use the appropriate second order equations to find the rate constant. And by the way, don't forget to put some units on that rate constant. And then tell us how much time it's going to take to go from 0.9 molar all the way down to 0.1 molar. Okay, so see if you can use a second order set of equations to solve this practice problem. Okay, so you might want to pause the video now so you can look at the details of the problem. Then we're going to have you do here a second practice problem. This second practice problem is going to require you to do some graphing. Okay, this is really the way that scientists determine the order of a reaction. The method of initial rates is okay, but it does have some limitations. The real way scientists go about finding the order of a reaction is to collect concentration data over a broad range of time. So here we have a table of data where the concentration of C4H6 is monitored over 5,200 seconds, as you can see from the chart. What we want you to do, and again, you have to do this with a piece of graph paper, or if you want to use your graphing calculator, that's fine too. But you need to figure out whether this reaction is first order, and if it's first order, the straight line relationship, as we now know, will be the natural log of the concentration information versus time. Or maybe it's second order, in which case the reciprocal of concentration versus time will turn out to be straight. Or maybe it's 0th order, and straight up concentration versus time will be a straight line. Only one of these three scenarios will produce a line that's straight. And of course, the slope of that line can be used to get the rate constant. Now, if you don't set the graph up correctly, on a small piece of graph paper, curved lines can kind of look straight, so you're going to want to make sure that you either use your graphic calculator to get this really accurate, or set up a piece of graph paper, maybe in like a landscape format, and make sure you make yourself a nice big graph. So again, on Thursday, come in with your answer for the first practice problem, and come in being able to talk about which graph, natural log, 1 over A, or A versus time for this particular problem and this particular set of data, gave you a straight line. All right, that'll do it for now. We will see you later.